In this video, we're going to talk about how to determine empirical and molecular formulas. So the first thing that we will talk about is percent composition. Now, when a compound formula is unknown, measuring the mass of each of its constituent elements is often the first step in the process of determining the formula experimentally. The result for this measurement permits the calculation for the compound's percent composition, now defined as the percentage by mass of each element in the compound. Now, for example, let's consider this gaseous compound composed solely of carbon and hydrogen. So the percent composition of this compound could be represented as percentage of H will be equal to the mass of H, which is hydrogen, divided by the mass of the compound. Then you multiply by 100%. What of the carbon in it? So with the carbon, we have percentage of carbon will be the mass of carbon divided by the mass of the compound. Then you multiply by 100%. So let's say in an analysis, we have 10.0 grams of the sample of this gas, which shows that in this 10.0 grams, it contains 2.5 grams of H, and maybe it contains 7.5 grams of carbon, which is C. What will be the percent composition for each of the H and the C? As we said, to calculate for H, let's look at the H first. So percentage for H will be the mass of H. The mass of H is what? 2.5 grams of H divided by the total mass of the compound, which is 10.0 grams, which is the compound. And then you multiply by 100%. Now with this, if we should calculate it, we should get 25% of hydrogen, which is H. Now, what about carbon? So carbon, we have the mass to be 7.5. So percentage for carbon will be equal to the mass of carbon, which is 7.5 grams, divided by the total mass for the compound, which is 10.0 grams compound. Then multiply by 100%. Now, when we calculate this, we should get 75% for carbon. Now, let's look at another example. So, in this example, we have a total mass to be 12.04 grams of a sample of a liquid compound. So, this is a liquid compound. Now, this liquid compound contains carbon, hydrogen, and nitrogen. Now, in this total number or total mass of this compound, carbon, which is the C, has its mass to be 7.34 grams. The hydrogen has its mass to be 1.85 grams. And lastly, the nitrogen, which is N, has its mass to be 2.85 grams. So what is the percentage composition for this compound? If you really understand the previous examples that we did, you can pause the video and try to do this on your own. Now let's look at the solution. So to calculate the percent composition, we are going to divide the experimentally derived masses of each element by the overall masses of the compound, then convert them to percentage. So let's do that. So for the C, so percentage of carbon will be the mass of carbon, which is 7.34 grams of C, divided by 12 the total mass of the compound, 0.4 grams of the compound. Then you multiply by 100%. Now when you do this, you should get 61.0%. What of the hydrogen? Percentage of hydrogen. So that will be 1.85 grams of C divided by 12.04 grams of the compound. Then you multiply by 100%. Now when you do that, you should get 15.4%. Then lastly, nitrogen. So we know that the mass of nitrogen is 2.85 grams of nitrogen divided by, so this to be H, 12.04 grams of the compound. Then you multiply by 100%. Then when you do that, you should get 23.7%. So the analysis results indicate that the compound is 61.0% of carbon, 15.4% of hydrogen, and 23.7% of nitrogen by mass. Okay. Now, do this on your own and let me know your answer. You can pause the video and try to do this on your own. So let's say we have a sample of gaseous compound containing, and now the total mass of the gaseous compound is 24.81 grams. Now in this compound, we have only carbon, oxygen, and chlorine to be determined. So for carbon, we have, which is C, we have the mass to be 3.01 grams. And with oxygen, which is O, we have the mass to be 4.00 grams. And for chlorine, which is Cl, we have the mass to be 17.81 grams. Now you can pause the video and try to do this on your own. So if you have done it, you should be getting the answer to be 12.1% of carbon, 16.1% of oxygen, and 71.79% of chlorine. Now let's look at another topic: how to determine percent composition from molecular or empirical formula. So determine So we are going to determine percent composition from molecular or empirical formula. Now, percent composition is also useful for evaluating the relative abundance of a given element in a different compound of known formula. So as one example, we consider the common nitrogen containing fertilizer, which is ammonia. Okay, and we also look at ammonium nitrate. So we look at ammonia, which is Na3, then we look at NH4NO3, then we look at urea, which is CH4N2O. So the element nitrogen is the active ingredient for agricultural purposes. Okay, so let's look at the ammonia first. So when you look at the molecule of ammonia, which contains one nitrogen atom weighing an amount of 14.01 average mass unit, okay, and three hydrogen atoms weighing total of 3 times 1.008 AMU. Now you combine it together, you get 3.024 AMU. Okay, now the formula mass for ammonia is therefore, so when you look at the nitrogen, so the nitrogen is 4.01 AMU. Then you look at the hydrogen, we will have 1 or 3, so we have 3 inside, so 3 times 1.008. okay, and when you multiply this, we should get 3.024. So the formula mass will be 14.01 plus 3.024. Together we should get 17.03 AMU. And 8% composition is, okay, 8% composition. Now we can see that we've gotten the total mass from here, 17.30. So we can use this to calculate 8% composition. Now, so to calculate 8% composition, we have percentage of nitrogen will be the mass of nitrogen, which is 14.01 nitrogen, divided by the total, which is 17.03 NH3. Then you multiply by 100%. When you do that, you should get 82.27%. What about hydrogen? So hydrogen, you should get, the hydrogen we got 3.024. It's not 1.008. The reason why we had 3.024 is we have 3 hydrogens of 3 atoms of hydrogens. Then we multiply them, we got the 3.024. So remember, then we divide it by the total, which is 17.03 of NH3, multiplying 100%. Now when we do that, you get 17.76%. okay, so this the same approach we can use to calculate for the NH4NO3 CH4N2O. okay, so you can pause the video and try to do that on your own. Okay, now let's look at another example. Let's say we have an aspirin. We said an aspirin, the molecular formula is C9H8 then O4. So what is 8% composition? Okay, now to look at that, we have to calculate the total mass. We have to know the total mass. So as we did earlier on, or as we had done in our previous video, we said the molecular mass for aspirin is 180.59 grams per mole. Okay, now from here we can determine the molecular or the percent composition of carbon. So we have carbon, percent of carbon, which will be 9 moles, multiplying the molecular mass of, or the molar mass of C, divided by the molar mass for the whole compound, which is C9H8O4 times 100%. Okay, so we have 9 moles of the carbon, or the C. Then we multiply by the molar mass for C. Okay, now if we should do that, we should get 9 times, what is the molar mass for C? 12.01 grams per mole, divided by, what is the total molar mass for the compound? 180.159 grams per mole times 100. And so the percent composition for carbon is 60.00% for carbon. Let's look at hydrogen. So hydrogen, we have hydrogen will be equal to, how many do we have? How many atoms do we have? So we have 8. So 8 moles times the molar mass for H divided by the molar mass for the compound, which is C9H8O4 times 100%. So we have 8 times the molar mass of H, which is 1.008 grams per mole, divided by the total, which is 180.159 grams per mole times 100%. So the percentage composition for H will be equal to 4.476% hydrogen. Now let's look at the last one, which is O. So for the O, we have, how many do we have for the O? We have 4. So that will be 4 mole times the molar mass for oxygen divided by the molar mass for the compound, which is C9H8O4, then multiply by 100%. Then when we do that, we should get 4 times oxygen. The oxygen is 16, so 16.00 grams per mole, divided by the total, which is 180.159 grams per mole times 100%. Then when we do that, we should get oxygen to be 35.52%. So that is for oxygen. Now note something here. Now you can note that when we sum the percentage, we should get 100%. Okay, so when we sum the first one, we got 60%, right? So 60.00. The second one, we got 4.476. And then the last one, we got 35.52. So when you sum it, we should get 100%. You should get 100%. Okay, so when we run this, we should get 5, right? Then so that'll be 40, so that'll be 100%, right? We can get 100%. Okay, now try this on your own. calculate the percentage composition for each of these elements in the compound. So try this FeO3. FeO3. Okay. Now let's talk about the last topic, which is how to determine empirical formulas. Now, as previously mentioned, the most common approach of determining compound chemical formula is to first measure the masses of its constituent element. But there's one thing that we have to keep in mind, that chemical formulas represent the relative numbers, not masses, of atoms in the substance. So therefore, any experimentally derived data involving mass must be used to derive the corresponding numbers of atoms in the compound. Okay, so why do we do this? We do this to accomplish using the molar masses to convert the mass of each element to number of moles. Now these molar amounts are used to compute whole numbers ratios that can be used to derive empirical formula of the substance. So now let's consider this example. Okay, let's say we have 1.71 gram of carbon, and we have 0.287 grams of hydrogen. What will be the corresponding atoms? So with the corresponding atoms, we have 1.71 grams carbon multiplying the 1 mole of the carbon divided by 12.01 grams of the carbon. So when we do this, we should get 0.142 mole of carbon. Then when we do for hydrogen, we should get 0.287 grams of H multiplying the 1 mole of H divided by 1.008 grams of, then we should get 0.284 mole of H. So this compound may be represented by the chemical formula C 0.142, then H 0.284 per convention. Okay, per convention. So this formula contains whole number subscript, which can be achieved by dividing each subscript by smaller subscript. So in here, what is the smaller one? It is this one. So we just divide each side, which is the number. So with this number, this is the smaller one, so we divide by the smaller number. So 0.142 divided by 0.142, which we should get 1. Then 0.284 divided by 0.142. When we do, you should get 2. So now the formula becomes C1H2. We don't bring the 1 because it's just 1. 1 is 1. So it's CH2. Very simple. Very, very simple. So let's consider another example right here. Let's say we have 5.31 grams of Cl and 8.40 grams of oxygen. Okay. Now, following the previous formula, when we do it, we should get. So let's do it. Let's just do it to make it safer. Or if you pause the video and do it, you should get, for this one, you should get 0.150, right? And for the oxygen, you should get 0.525. Okay, so now we look at the smaller number. The smaller number is 0.150. So we divide each by the 0.150. Okay, so when we divide 0.150, this gives us 1. So we have Cl to be 1. Then we divide 0.150 then this will give us 3.5. Okay, so here we'll be having, that's for the O, right? So we have Cl1, then O 3.5. Okay, so now in this case, dividing the smaller subscript still leaves us with a decimal subscript in this one, which is 3.5. Okay, so we can do this by multiplying each side. We want a whole number. So how do we get a whole number? So we just multiply this by 2, then multiply here by 2. Okay, so we come to get Cl2O7. Very simple, because when we still divide it, right, you should get Cl3.5. so far as we want to get a number to be able to name our compound, okay, we get Cl2O7. Now this is the end of this video. I will see you in my next video. Okay, thank you for watching. If this is your first time here, subscribe, share, and put your comment under the comment section. Thank you for watching.